IRMS, sorry.
Hey guys. First of all, sorry I was not here for the exam. Arno explained to me a little bit, about writing clean. I announced it in the class, 5 point, extra point for writing clean and override, You didn't have to tell you because I told you in the classroom, On the problem number 3, looks like there was some confusion, how you can recall it here. Looks like some people, they thought, yeah, it would be logical if somebody thinks this is A3. My intention was to keep all this area like A1, but if somebody consider this one A3, because this one looks the same, same cross section, still I'm going to go with that one, I'm not going to subtract any point for that one. I solved the problem 2 times, but make sure that one is covered. But AG and LG is not acceptable if somebody used, I don't know, A3 over A4 for the AG. Is not acceptable because clearly it says there's the AG this much and LG this much, That one is not acceptable because I use the A3 or A4. Here's the printing flux. I didn't ask you to model it, just I give you the number. I said, okay, AG is this much, Remember we said the flux is going to open up, right? So effectively the AG is going to be bigger than the L, here is A3 and A4, And I think problem 2 was pretty straightforward, I think. How about problem number 1? How many of you guys didn't get that one? Problem number 1, it's like, this one was like a multiple choice question, it's going to take like maybe 5 minutes to solve it, maybe 5 minutes, not more. Good idea? Just think about it, how simple it is. Right, and I think the iron is ideal, right? So basically when the flux comes here, let's do it this way before going there. Let's say we have a circuit, right? And we have something here and we have a 3 resistors, right? When the current comes here, right? Part of it is going to go here, part of it is going to go here, part of it is going to go here, right? And look at here, when we have flux, this flux is coming from here, right? And we said it's a straight line, there is no fringing flux, So basically this flux is coming here, part of it is going to go here, part of it is going to go here, part of it is going to go here, right? Just model this one with one reluctance, right? Because the gap is this much. Model this one with another reluctance, right? And model this one with another. So circuit is going to be like this. I cannot remember what did I ask. To find what the circuit is like. Energy, I mean something like that. So basically this is 4, 4, 4. Yeah. So the only things here is a 2G. So basically if this one is R, this is R, this is a 2R. So look at this like 2R, yeah.
And then okay, I modeled the 2 outside ones and this parallel itself.
This 3D curve.
Yeah. No, I combined the 2 so I didn't have like R, R, and
That's
2R.
fine. You just put R over 2 there.
Yeah.
That's fine. You can do that. This one is like, as I said, 5 minutes question more.
Could you model it a different way? And then depending on the cross-sectional area and the length.
Or turn it into 3 circuits?
Say.
Did you turn it into 3 circuits?
No.
Well,
I was just going to say, if you have this one up here, and then in series with the long one here.
But you're not serious. See, the flux is coming here. In what I'm doing, when we say with electrical circuit, we say these two circuit, the current is the same for both of them, right? The current goes this way. Yeah. We say they are parallel if the voltage is the same, right? We say it's parallel if the voltage is all the same, right? But here, look at here, the flux is, look at here, this is the voltage, right? For this one and this one and this one, all the same. Or you can say the flux is coming here. It's going, part of it is going this way, part of it is going this way, part of it is going this way. Problem 3 was very similar to one of the homeworks you had, but the curve was like this. The curve was like this. Remember? The VH curve was like this. This one is a little bit different, just the curve is like that, and the numbers are different, I will send you the solution. I'm gonna grade everything this weekend, for sure. And Tuesday you're gonna have me grade. So let me see what did we cover in the last one. We talked about the induction machine, right? I'll give the third homework page tonight, if I can stay off and I'll put it together. I'm sure we'll get lag, you know. Let me see. I'm not sure if I'm gonna stay for the discussion, you know, if I'm passing out, I'm gonna say let's go, but if I can, I'm gonna go through a few examples, you know. So we went through the basic of the induction. You know, I left Wednesday afternoon, and the overall trip is about like 30 hours. Go there and come back again. The flight is about 20 hours, but you know, with the layoff and all those kind of things, you know, it's only 30 hours. You know, when you go there, you're changed 12 hours. You know, your time is changed, and your body needs about like at least 4 or 5 days to get used to it. You know? And as soon as I was almost there, then I have to come back now. You know, and again now my body is kind of confused on what's happening. How many laps have you had right now? How's the lap? How's the lap? Do you like it? Hopefully not very bad, but you guys are happy. But is the lab good? You know, I'm not sure. Because it's very safe lab. You know, you can say now unless you want to kill yourself, you can. But it's pretty safe lab. You know, you cannot do any damage to yourself. And this is the first step we have this thing. You know, and I'm happy we have it because without lab, we all the paperwork and this kind of thing, and it's not that good. Today we are going to start the. We talked about the basic of the induction machines, how they work. We talked about the little bit, you know, voltage induced in the rotor because of the difference, you know, between the rotating speed of the rotor and the synchronous, you know, speed of the stator magnetic field. So we are going to have the frequency in the rotor winding. We call it FR, which was equal to SFS. Right? If you can remember it. Fs was the frequency of the stator winding. Now we are going to go through the equivalent circuit of the induction machine to see how it's going to work. You know, induction machines, they are AC machines. They are even the frequency is different in the rotor from a stator, but still there are two AC windings. And if you remember from the 188, we started with transformer. Transformer also is the AC machine. It has a two winding, but the only difference is both sides they have the same frequency. Because in transformer, both windings they are stationary. They are not moving because any frequency difference. Now let's see how we can model this one. You know. So we'll start with the equivalent circuit of the induction machine. So we have a state. I'm going to derive for one phase. You know, you are familiar with the three-phase system now, and the machine is balanced. So I don't have to draw the circuit for 3 phases because we can solve it with for one phase. If I need phase B, 120 degree delay. If I need it for phase A, C, I'm gonna bring it ahead 120 degree, right? So I'm going to draw only one phase of the machine. So we have an induction machine. The stator, let's assume this one. Let's say this is the motor. The stator is clocked to a 3-phase, clock, right? So, and the stator has resistance, right? Because the winding has some resistance, and it has the inductance. Why do we have inductance? Very well. We have a winding and we have the core is going to end up with some inductance, right? So, and again, going back to the transformers, remember? So we said we have a magnetization flux going this way, right, in the core, and we have some leakage here, right? Part of this, flux is going to go through the air, right? The same story again here. So basically, it's going to be like RS. RS is the resistance of the stator winding, phase A. But phase A, phase B, and phase C, they are all the same, right? Now, you are going to have a leakage inductance. We call it XS, but XS is LS times omega. LLS. LLS is the leakage inductance of the stator winding, right? If everything is perfect, then we have the stator winding. When it generates flux, all the flux is going to go through the iron of the stator, right? But because it's not perfectly, ideal, some of the flux is going to go through the air, right? That won't be showing with LLS, right? The next thing we are going to have, exactly like a transformer. Remember what we said? We said we are going to have a magnetization inductance, right? And so I still am on the stator side. Where was the core loss for the induction machine? Because the core loss was in the stator, right? Because we said the frequency in the rotor is very, very small value. And we know the core loss depends directly to the frequency, right? If the frequency is almost zero, there is no core loss in the rotor, right? And we said S, the slip was like 2%, 3%, very, very small value. We said, okay, almost more than 95% of the core loss is going to be in the stator, right? So, like transformers, we said we are going to show the core loss with a resistor. We call it RC, if you remember, right? And we are going to have a magnetization inductance XM, right? See, this is exactly like a transformer. So those ones are remembered. The resistance of the winding, the leakage inductance of the winding, right? And it's the core loss, because we have a hysteresis and eddy current loss, and the magnetization inductance. This XM is a result of the main flux is rotating, you know what I'm saying? So we have this. Now, so we came from a stator phase A, we're coming in, right? We went through the stator. Now we're going to go through the rotor, right? So the stator is one winding, rotor is another winding, right? So basically it's like a transformer. As I said, the only difference, this winding is rotating, right? The only difference between this one and the transformer, three-phase transformer, the secondary winding, which is rotor here, is rotating, right? Let's call this one, we'll call it T1 here. Let's call the number of turns here NS, number of turns here NR, and put the dots here and dots here, right? So if here is the E1, so the voltage here also is going to be like this, right? Let's call it E rotor, ER, right? Again, rotor winding has two things. One is the resistance of the winding, and you are going to have some leakage inductance, right? And see, I'm not going to put another magnetization. First of all, there is no RC over there, because in the rotor we don't have any core loss. And I'm going to put one more here, because we put everything in this one, all the magnetized, like a transformer. If you remember when we had this one, we didn't put two XM, one XM here, one XM over there. We put only one XM, one side. We can transfer it in any side we want, right? Now, here we are going to have RR and X. Here. If it's a squirrel cage machine, so basically the is the rotor, and these are the, it's not, usually it's not a winding, it's a copper bar. They put a copper bar, instead of winding, they put a copper bar, and they are like this. All the way, around this way. There is one ring here. It is a squirrel cage, right? And there is another ring here. Just I'm gonna for both these. There is a squirrel cage and there is a wound rotor. Wound rotor means they bring 3 wires from here out. They kind of categorize this one, 3 wires coming out. Even in the wound rotor, for the operation, they put all these 3 in, they short all these 3. In the squirrel cage, it's shorted here. We don't have access to this one, to this winding. But in the wound rotor, we have access to one side of the rotor. One side is shorted in the rotor, the other side is available to us. And simply you can see, the squirrel cage machine, they are much cheaper than the wound rotor. Why? Because the wound rotor, you have to bring these wires out, right? Like the DC machine, they have to have a commutator. But see, this one is moving. Think about it. This one is moving. Now, you have to come up with kind of a arrangement. You can bring these 3 wires out. They put a slip rings for that, like very similar to the commutator. So those things will make the machine more expensive. The squirrel cage machine is the cheapest one compared to the wound rotor and compared to the DC machine. But at the end of the day, either one, they're shorted here. I'll tell you what's the difference. Like another problem with the induction machine, like a DC machine is a starting. Remember, we went through one example for the DC machine. If we don't put any resistors instead with the armature, the current will go 10 times of the rated current of the machine. These machines also, they have the same problem. Induction machines, they have the same problem. The starting current is about like 6, 7, 8 times of the rated current. So to limit that current, all time, if you would have access to this one, we will talk about this one later. We'll add some resistor here, like exactly what we did for the DC machine, to limit the current. And gradually we take that current out, that resistor out, exactly what we do. But my point is, at the end of the day, when we get to the steady state, all short. We're not going to put any resistor in the rotor winding because it's going to cause, power loss. It's going to bring the efficiency down, right? So either if it's a wound rotor or is a squirrel cage, it will be short. So basically, if it's here short, it means it is short, right? Right? So if it's the wound rotor, for example, it's going to be like this. It's going to be like a rail stud here. You can put it here. You can move this one off, right? When you come here, again here is shorted, right? Initially you can put some resistor in the circuit, right? To limit the current, and after that you can move this one off to short the resistance, right? So, but to prevent confusion, see just here is short. Now, let's name all these currents here. Let's call this one BS. So basically this one will be connected to a source. The reason I use the motor model, this is a motor model. You can see we connect this one to voltage, current coming to the machine, IS. Because induction machine, mostly, I'm not going to give you the percentage, but I think like 80% or maybe more, they are used as a motor. So that's the reason I went with the motor model, The current is going to the machine. If it's a generator, the current is going out. There is no difference. Because mostly, especially in this course only, we're going to have the induction motors. I use the current to go toward the machine, toward the inside the machine. I mean, the machine is acting like a motor, right? Now, this is a VS, this is the IS, but phase voltage. Keep in mind. Let's say, for example, they said we go look at the plate of the induction machine. They said V nominal is 208. 208 is a line voltage, RMS. So if you are going to put it in this model later on, you are going to solve it. So basically, this one is going to be 208 over the square root of what? 3, because it's a phase. You said give it an angle 0, for example, because it's the easiest one you can solve.